Hey, today we're going to be looking at Penrose tilings. This is a specific kind of tile um, that is using special tiles that we'll look at. This is building off of my last presentation on tessellations and different tilings. So first, some background information. In 2011, Dane Checkman was awarded a Nobel Prize in Chemistry for the revelation of quasi-crystal structures. These were observed first during the production of aluminum manganese alloys, and what they found was that these quasi-crystal structures create a non-periodic pattern, and more specifically, they create an aperiodic pattern, and we'll talk about those differences here in a little bit. So previously, crystal structures were restricted to and only known to have 2, 3, 4, and 6-fold symmetries. However, with the discovery of the quasi-crystals, there was the introduction of pentagonal symmetry within these quasi-crystal structures, which is really actually very, very neat and quite miraculous in and of itself. So some basic definitions, just review kind of from my last presentation. A tile is a geometric shape that overlays a plane with no gaps or overlaps. And tilings are the plane that is covered by tiles in a way that there are no gaps or overlaps. And so we see these three figures at the bottom. Remember, these three are the three regular polygons that can create a tiling in and of themselves. So we have the square, the triangle, and the hexagon. These create tilings with themselves and with each other. But specifically, what we see here is them tiling with themselves. All right, the first definition we have is called a periodic tiling. This is a tiling where you can outline a region that tiles the plane by translation, so we can shift this outline without rotating or reflecting it and get the same pattern that we have originally. So here you see I've outlined this star pattern with these triangles, best I could, obviously using PowerPoint. But what happens if you see when we shift that star pattern without rotating or reflecting it, it moves right onto the same pattern within that tiling. So that's really neat. So that's called a periodic tiling. So if you can translate the outline of a shape from region to region within the tiling and not change the outline of the shape, that's considered a periodic tiling. A non-periodic tile is that those that create a structure with no translational symmetry. And this one, you really just kind of have to go with me on this because this isn't a perfect illustration. But if you look at this original outline with this decagon here, basically what I'm going to show is that if we go from decagon to decagon, it's not an exact translational symmetry. Notice the orientation of the middle of kind of like the star figure coming out of the middle. It's not necessarily exactly the same as the others. So now again, this is only showing that there's not really a translational symmetry between the decagons. You could take any of these basic figures within this pattern and show the same thing. I just chose to do the decagon. Again, this is really subtle, and it's really, especially with this finite picture that we have here, it's not entirely clear that if we were to project this figure infinitely, that there would be no translational symmetry. But basically, I'm just trying to give you the idea of a non-periodic tiling and how it's different from a periodic tiling. Because with the periodic, you can take any of those outlines and move them anywhere in the structure and it would be the same figure. Whereas here we see that that's not the case with these decagons particularly. But again, this is really, really subtle and quite miraculous in and of itself. So just this is a general idea. Like I said, just kind of go with me on this one. Again, just this in and of itself is not a proof that there is no translational symmetry in this whole pattern. I just showed that there's no translational symmetry in the decagons, kind of in that circle, but you get the idea. Now, there are some tiles that can produce both periodic and non-periodic tilings. This is a special special kind of decagon that's caved in. And so what we see here is that it can create both periodic and non-periodic tilings. That should be kind of like an obvious observation here. We see that we could outline any of those decagons and translate it, and without rotating or reflecting it, it would land on another decagon. Whereas if we were to do that here, if I were to take this center red one and even translate it up just one, it would not fit onto that blue tile unless I were to rotate it or reflect it, but then that violates the rules of periodic tiling. So, but that is pretty neat that there are some that go both ways, and they can create both kinds of tiles. Aperiodic tiles are tiles that can only produce non-periodic structures. All right, so for this example, this basic figure right here is called the Sphinx. And what it does is we can use this basic figure of the Sphinx, and we can do 3 generations of it and rotate it and reflect it, and we get basically a larger super Sphinx, if you will. And that shows this non-periodic tiling. I cannot take this basic figure of the Sphinx and move it even over one tile and get the same figure without rotating or reflecting it. So this is a specific tile that will only create a non-periodic. There's no way I can use this shape to create a periodic structure. And lastly, what we see that's really cool actually is just a larger generation of the Sphinx to create another super Sphinx. All right, that's not enough supers, but again, you get the general idea. We've used a smaller Sphinx to create a bigger Sphinx, which is actually leading us into something which we'll use this idea later in a proof, and we'll refer back to this. This idea of having one basic tile creating a larger tile or existing within a larger tile of itself. We'll use that in a proof later. So specifically Penrose tiles. This is a pair of shapes that tile the plane aperiodically. And so these were discovered by Penrose, and basically we see 2 rhombi here, and these 2 rhombi are what create this basic Penrose tiling here. And again, there is no way that we can tile these periodically. That is why it's called that's why it's an aperiodic tiling. But it creates this really neat pattern. So what we see is that we can take a rhombus and show 2 other shapes called the kite and the dart. And these are really, really neat, and they can form their own tiles. And so for the Penrose tile to work, we have to label the kite and the dart with basically T's and H's, kind of like heads and tails, where T's can only line up with T's and H's can only match up with other H's. So part of your homework is basically to create and sketch out a rhombus, a kite, and a dart. What's really interesting here is to notice the role of the golden ratio, and notice the role that plays in the creation of these figures. And if you want to, you can use the decimal form of phi to just kind of give you like a general idea when you sketch it out. It is just a sketch, but it's really neat to see how that kind of plays a role in the creation of these figures. Also, what's really neat is that when you go through this, 36 degrees is the smallest angle measure, and no matter how you organize them, as long as you organize them appropriately, every angle measure is going to be a multiple of 36 degrees. So that's pretty neat. But here you see the basic kite formation right here, and then the basic dart formation on top. All right, so how does this exactly work? So what we do is we take the kite and the dart, and we can add these colored lines to them, the blue and the red. And by adding the blue and the red on them, that shows that we can only tile these in a certain way, that they have to match up in a certain way. So with these restrictions, that is another thing that makes it impossible to create a non-periodic tiling. So this is kind of hard to see right here, but you can see how if we were to take 5 kites in the middle and tile them together, how those match up, and then we can put some darts on top. And we'll go through this. You'll see a better description of this here in a minute. All right, so there are 2 basic patterns formed with the kite and the dart. There's a sun pattern and a star pattern. And these are the only 2 ways to create an aperiodic tiling with pentagonal symmetry. So I'm going to show you how I made some of these on my own. The first one is using the darts. We're going to create this star pattern. So you see all the blue circles are lining up together at the point. And we have this pentagonal symmetry here. You see the 5-pointed star. They're used to create the other. Now this is the sun pattern using the kites. So again, we line up the blue circles, or we're going to create a circle with the blue lines. And again, you see this pentagonal symmetry here, and the creation of that sun pattern. Now, one thing that's really interesting is that there's only certain ways to match these tiles. So what I've done is I've created this star pattern here, and basically what we're going to show is that you can't put a dart on top of another dart, because remember, we can't have any gaps or overlaps. So in order to do that, we're going to show that basically there's no way to fit a dart on top of a dart, because you see we have the overlap here. And that no matter how we do this, there's either going to be a gap or an overlap. And basically we go through this looking at each vertex here. And we see that there is, in fact, no way to tile these with all kites. So next, we just need to prove that Penrose tiles only create structures that are non-periodic, and they only create bigger tilings of themselves. So first, we have to prove that the tiles can form a tiling, which is what we just did with the star and sun patterns. Then what we're going to do is I'm going to show you that they can form super tiles. So those are going to be the next videos. I'm also going to show you how a kite and 2 half darts form a super kite. And then also any configuration that the tiles can be formed by the super tiles, and vice versa. This is called either inflation or deflation. So basically with any structure, you can make it bigger or you can reduce it smaller. So it follows that if we can make a super tile, then we can make a super tile, and so on and so forth. So consequently, we have any n level super tiles form an n+1 level super tile that always maintain that property. So that proves that we can form arbitrarily large configurations that are non-periodic. So what I'm going to show you here is the kite and the half dart. So what we see is that if we put two kites on a dart, let's go back, there we go. What you can see is you actually have this bigger kite pattern that is formed. All right, it's kind of like an inverted kite from the original one. And so you see that taking the 2 half darts, now we can't put one kite on top of a dart because then the red lines don't match up. And so we see that this kite is formed by the kite and the 2 half darts.